Hello, in this video we're going to talk about oxidation numbers. And oxidation numbers are closely related to electronegativity and charges on various ions, although they're not exactly the same as either of those. What oxidation numbers are, an oxidation number is a number assigned to each of the atoms composing a compound or an ion that's used to indicate the general distribution of electrons among bonded atoms in a molecular compound or polyatomic ion. You may have also heard of an oxidation state, which is really just another name for an oxidation number. So this whole thing we're going to talk about is really who, or which element rather, is seen as having the electrons. So oxidation numbers can help us in understanding where electrons go when a compound is formed or when a reaction occurs. You already know about electronegativity, and an element with a higher electronegative value is seen as having a greater draw on the electrons. So it's kind of related. Okay. When an element or a compound loses an electron, it's said to have been oxidized. Okay, and here's the part where your brain's gonna go, what? When an electron or compound gains an electron, it's said to have been reduced. And everybody's brain has a hard time wrapping around this concept because you're reading, okay, something gains electrons, but it's reduced in your brains. It just has a tough time with that. So I have this little thing that might help you remember these. It's a silly little acronym. Leo, as in Leo the lion, Leo goes grr. So Leo, lose an electron, oxidized, and grr, you gain an electron, it's reduced. So quite often, if you just remember this silly little saying, it's going to help you to keep these straight because they can be confusing. Okay, now let's make things a little bit worse. An element or compound that causes another to lose electrons is said to be the oxidizing agent. Okay, and the flip side of that coin, an element or compound that causes another to gain electrons is said to be the reducing agent. So a reducing agent is giving away electrons, and an oxidizing agent is taking electrons. Here's some rules that you may want to commit to memory or write down as you go through compounds and practice these. After a little while, you're just going to start to know some of these. Okay, where electrons are in polyatomic ions or molecular compounds is determined by the general rule of whichever is more electronegative gets the electrons. So here are the rules. If we have pure elements, for example, simply sodium, it's all sodium, nothing else in the compound, its oxidation number 0. Or if we have oxygen, just O2 or O3 or whatever, nothing but pure oxygen, no other elements involved in there, it's going to be 0. Same, any element, phosphorus, we got 4 phosphorus atoms bonded together, the oxidation numbers are 0. Okay, rule number 2. In a binary molecular compound, the more electronegative elements equal the charge it would have if an anion, negatively charged. The less electronegative element is equal to the charge it would have if a cation. Okay, so you remember your ionic bonding, that might help out with this rule. Rule number 3, fluorine is always -1. Rule number 4, which you're probably going to use more than any other rule, oxygen is usually equal to a -2. And of course, there are exceptions to every rule, except in a peroxide such as H2O2, hydrogen peroxide, in which case it is -1. Or when it's bonded to fluorine, then it is a +2. Okay, hydrogen is +1 when bonded to a nonmetal, and is -1 when bonded to a metal. Now, the vast majority of the elements in the periodic table are metals, so watch out for this one. Okay, rule 6 and 7 you're going to use with almost every single compound or ion, depending on whichever it is. The sum of the oxidation numbers in a neutral compound is 0, and the sum of oxidation numbers in an ion equals the charge on the ion. So these almost should be first, because with almost every one of these, you're going to be looking at these rules first, 6 and 7. So here's what we're talking about. If we have hydrogen bonded to chlorine, we have a rule that says hydrogen bonded to a nonmetal is +1. And let me go back here, rule 5. Let's look at rule 5. Hydrogen bonded to a nonmetal, +1. Okay, so the hydrogen, and let me just write that in here. Okay, so we've got hydrogen. I'm just going to put it right above it as a +1. And overall, this thing has no charge on it, right? Since overall this is neutral, okay, go back and look at the rules. We had a rule right here. Rule number 6, the sum of oxidation numbers in a neutral compound is 0. So the whole thing equals 0 when you put the oxidation numbers together, because there's no charge on it. So +1 plus whatever chlorine is equals 0. So that means chlorine has to be equal to -1, because a +1 and a -1 equals 0. Okay, let's look at the next compound here. We have carbon and 4 fluorine atoms. Okay, well, fluorine, rule number 3, let's look at rule number 3. Rule number 3, fluorine is always -1. Okay, we have -1. I'll just write that in here. And since we have 4 of them, that means that we can multiply by 4. And that's actually -4 right there. Now, since overall it's neutral, again, there's no charge, just as we had in the last one. So it has to equal 0. It's neutral, no charge. So if this fluorine part of it is -4 and altogether it's 0, that means the carbon part of it has to be +4. Okay, here we have a compound that has 3 different elements in it. So again, as we did before, let's look at the rules and see what we can figure out about this. Okay, oxygen, rule number 2, or excuse me, rule number 4. Rule number 4, oxygen is usually equal to -2. Okay, we don't have a peroxide and we don't have fluorine in this compound. So each oxygen is going to be -2. And we have 3 of them, so we can multiply that by 3. And that's going to give us a -6. Okay, since overall this whole thing is 0, why don't I just put that in right away? There's no charge on it, so I'm going to put my 0 in there because they all have to add up to 0. Okay, we've got the oxygen taken care of, so we have hydrogen and chlorine. We need to look and see if we have rules for those. Okay, let's look back here. We have a rule for hydrogen. Hydrogen is +1 when bonded to a nonmetal. Okay, oxygen's not a metal, chlorine's not a metal, so hydrogen's going to be +1. So let's go back here. I'm going to write in a +1 for the hydrogen. Okay, so far what I have, I've got -6, and I can put that in right there. I got -6, because -2 times 3 is -6, +1 is -5. So it has to equal 0, meaning that chlorine must be +5. So +1 plus 5 is 6, and -6 equals 0. I think you're starting to catch on now to how these work, and you could probably go through and try some without the rules. Let's do that. Okay, let's find the oxidation number for one atom of the underlying element. Okay, so we have oxygen bonded to fluorine. Well, let's look and see what our rules say. We have rules actually for oxygen and for fluorine. So let's go back, look at our rules. Okay, rule number 3, fluorine is always a -1. Okay, so let's go back and we'll write in, and maybe choose a different color so I can see it a little better against this background. Okay, so fluorine, -1, and I have 2 of them, so I'm going to go times 2. And overall, there's no charge on this. So all of these oxidation numbers have to add up to 0 in this case. Okay, so if I've got -1 times, okay, so that's -2. Okay, and I have oxygen left. So it's going to have to be +2 for that oxygen. Now remember we had a rule for oxygen. Let's go back and look at that for a minute, because it said oxygen is usually a -2. Well, how come this one has to be +2? Let's go back and look. Okay, oxygen is usually a -2, except when a peroxide such as H2O2, it's -1, or one bonded to fluorine. So then it is a +2. Okay, so we haven't violated any rules in doing this. We came out with the right answers here. So our answer, underlined element, +2 for oxygen. Okay, let's pick up the pace here a little bit. We know overall there's no charge on this, equal to 0. And by now you probably have it down that the rule for oxygen, usually a -2. We have hydrogen, we have a rule for that. Bromine and oxygen, neither one is a metal, so it has to be +1. So +1, -2, you put those together, it leaves us -1, meaning bromine must be a +1, our underlined element, so that's our answer. Okay, again, no charge, so it's equal to 0. Oxygen, usually a -2. Have 2 of them, so we can multiply by 2, giving us -4. Okay, so that means the sodium part of it has to be +4, right? But what we're looking for is the charge for one atom. Okay, we have 2 sodiums, so we're going to have to divide that +4 between these 2 atoms. So our final answer for one sodium atom has to be +2, +2 for each sodium. And finally, okay, here we go. We finally have one with a charge on it. So that means that this isn't going to equal 0. It's going to equal what that charge is. That -2 is up high. That stands for the charge. So I'm going to put equals -2 up here. We're going to use the same rules. Okay, oxygen is -2. Each oxygen's -2. So I'm going to put -2 right here. We have 3 of them, so times 3. Which gives us -6, right? Now, we have to combine this -6, put -6 up here, with something that will make our answer be -2. Well, the only thing that works there is a +4. So that's our answer, +4 for the sulfur oxidation number. All right, let's move on. This is going to be the last thing we talk about for oxidation numbers in this video. Oxidation numbers can be used to kind of tell us who's got the electrons, and this can be applied to chemical reactions. We're not going to go into that in this video. We're just going to do the compounds as we just did. Oxidation numbers can also be used in formulas and names, and in previous videos we've talked about different naming systems. So rather than read all of this, I'm going to skip down here. We're going to talk about the stock system. We have sulfur 4 oxide. Another name for it would be sulfur dioxide. And the way we get the sulfur 4 oxide out of SO2 is by using oxidation numbers. So we've got an SO2 here with no charge on it. So I just write it right up above. Well, that color's not going to work. Let's try this. And so, hold on here. Get rid of that. And let's try a color that shows up better on this background. Okay, no charge on it, so it equals 0. Okay, we know that each oxygen is -2, and we have 2 oxygens, so times 2, giving us -4. So since it has to be added with whatever the oxidation state for sulfur is to equal 0, that means sulfur has to be a +4. So if you look over here, sulfur 4, we just found 4, sulfur 4 oxide. And so that's how this can be used in the stock system. Okay, well, here we have sulfur and oxygen again, different combination. Again, no charge. I'll write this one down below. Okay, so no charge, equal to 0. Each oxygen still equal to -2. This time we have 3 of them, so -2 times 3, giving us -6. And so as you've probably already figured out, the sulfur has to equal a +6. So if we were naming this using the stock system, sulfur trioxide would now be called sulfur 6 oxide. So I guess you can see that there are a few uses for these oxidation numbers, and the uses for them actually go beyond what this video is going to do, but for today we're going to call that good. Thanks for watching.